Okay, this is the second video in the series on Introduction to Differential Equations. And here we'll start with the definition of an initial value problems. So in an initial value problem, basically we want to know a solution of a function or a dependent variable y. So we want a function y of x that's a solution to a differential equation that also satisfies certain initial conditions. Now, usually in engineering, initial conditions are referred to time, which is why they're referred to as initial in this textbook. So what you want to know is what was the value of y and its derivatives at the zero value of time, or when the problem began. However, it doesn't have to be time and it doesn't have to be zero. So it could be space. If y is a function of x and x is a spatial variable, then as long as we have some point in space where y and all of its derivatives are defined and known for that particular point, then basically we can get a solution to the initial value problem. Sometimes, in a more general sense, this is referred to excuse me, as a boundary value problem, and rather than an initial condition, it is referred to as a boundary condition. You'll see it both ways. In electrical engineering and in the courses that I teach, almost exclusively we're talking about initial values and we're talking about initial conditions on time. But for example, if you have electromagnetic fields or some kind of thermal problem that has spatial characteristics, then you can also have boundary conditions in space. So basically, the initial conditions are specified that at this point, x sub 0, the value of y is known, y sub 0, and the value of its first derivative is known, and the value of its second derivative is known, and so on, all the way up to basically a definition of the initial condition on the derivative that is one lower than the differential equation. So, for example, if you had a second order differential equation, which would mean you had a second derivative, you would need a boundary condition on y, and you would need a boundary condition on the first derivative of y. You would not have a boundary condition on the second derivative of y. So the number of boundary conditions is going to be equal to the order of the differential equation. So, first of all, when we're solving such a problem, we have to think about whether the solution exists and whether it's unique. So existence means does the differential equation have a solution, and do any of those solution curves pass through our initial condition point x0, y0? And secondly would be uniqueness, meaning there's only one solution curve that passes through that point. So there are some theorems that determine what is sufficient to guarantee existence and uniqueness to a first order initial value problem. Basically, that would say that the function x and y and df dy are continuous on some region R for the interval I0, and this point x0, y0 is contained within I0. So once again, that's mathematics speak, which we're not terribly concerned about memorizing or proving. We'll just accept that and move on. So here's an example of a first order initial value problem. So I have y is equals to c to the ex. That's a one parameter family of solutions that satisfies this differential equation y prime is equal to y. So we'll just take that for now without going through an example on how to solve that differential equation and get this result. We'll just accept that this is the result. The first thing that I want to point out is if you take this c e to the x and you plug it in for y, and then if you take its first derivative, y prime, you'll get this back, c e to the x. So you'll have c e to the x is equal to c e to the x, which is what we were talking about in the earlier lecture, that you basically then have an identity. All right, so what we want to do is we want to find a solution of the first order initial value problem that has an initial condition at 0 equal to 3. So basically what you do here is you substitute 0 for x, and then you evaluate what c would have to be in order to make y at 0 equal to 3. So when we substitute that in, we get 3 is equal to c e to the 0, and we know e to the 0 is 1. So that would tell us that c, our parameter to solve this initial value problem, has to be 3. So y will equal 3 e to the x. Okay, a second order initial value problem would have two different solutions. So here is the differential equation, x double prime plus 16x is equal to 0. It's a function of time. When we solve that second order differential equation, which we'll do in a later chapter, what you get is you get two different solutions. So what we'll find in a later chapter is that for every order of derivative, we have to have a unique, at least the possibility of that number of unique functions that will satisfy the differential equation. So we have a cosine of 4t and a sine of 4t, and so the general solution then would be the sum of those two. And once again, we'll cover all this later. Right now, we're just looking at the meaning of initial value problem. So we have this solution. X is c1 times cosine of 4t plus c2 times sine of 4t. And just as a reminder, when you have a second order differential equation, you will generate two constants. So that's exactly what we have here, c1 and c2. Now, in order to get the solution, in order to know both of those constants, since this was a second order differential equation, we'll actually need two initial conditions. So we need an initial condition on x and an initial condition on x prime. And notice that initial condition is specified at pi over 2, at the point pi over 2. So if we take that point pi over 2 for x and we substitute that in for the first and second derivatives, so basically you would go back to your original equation. So you go to your solution that has x equal to this sine and cosine function, and you plug in pi over 2 for t, and then x basically would be minus 2. So you would have minus 2 is c1 times the cosine of 2 pi plus c2 times the sine of 2 pi. This one is going to go to 0, and so you can then determine the value of c1. To solve for c2, we now need to take the first derivative of this equation because our other boundary condition is specified for x prime. So you take the first derivative of your solution, you substitute pi over 2 for t, and then you substitute 1 for x prime. And if you do that, you'll find that c2 is equal to 1/4. So then the solution of this initial value problem is given as follows, where we have substituted in for c1 and c2. All right, we're just very briefly going to touch on differential equations as mathematical models because typically in textbooks like this, they tend to use more examples from the physical sciences and not so many from engineering. So we'll try to introduce our own examples from engineering throughout the course of the semester. But basically, differential equations typically come from physical laws. So generally, you will have a physical law, often empirically discovered or experimentally discovered, and it will provide a differential equation that actually gives you a model, and this occurs in biology, physics, chemistry, and throughout all of the branches of engineering, which are often viewed as applications of the three general scientific fields. So basically what generally happens is you start a modeling process by making some sort of assumption. And then you express those assumptions in terms of differential equations. So I might, for example, make the assumption that population growth in a particular group is a power function. And so if I let y be the population, then dy dt would be the change of the population as a function of time. And so I could then come up with some hypothesis that describes the rate of change of a population. So I then have to come up with an equation for that And often that equation contains first or second or even higher order derivatives. It's unusual in the physical sciences to have much higher than a third order derivative. It's not impossible, but mostly much higher than a third order derivative becomes more of a mathematical construct and doesn't as often model physical systems. In fact, usually second order differential equations are generally what you tend to find in engineering systems. So once I have the mathematical formulation, I have some differential equations. It could be multiple variables. It could be multiple dependent and independent variables. In electromagnetic fields, you tend to have field strengths and electric potentials as dependent variables. X, Y, Z, and T are often independent variables, so it's space and time, and you may have derivatives in all of those in order to describe fully the field. So once you have the mathematical formulation, which usually comes from physical laws that have already been developed, you then solve the differential equations. And here is where boundary conditions and initial conditions really come into play, is that different systems will have different specified initial conditions or spatial boundary conditions. And so you have to employ those in order to obtain solutions. You then obviously will display what the model predicts the outcome will be. You then check that model with known facts. It either will or will not fit the problem well. At that point, you then either have to change your basic assumption or you have to increase how finely you define the model. Maybe you do need to add that third derivative term. Maybe you need to add a fourth derivative term. Maybe there's some nonlinearity in the system that you need to take into account. Sometimes the fundamental hypothesis can be wrong. And one of the things that I've observed, especially in graduate students who are coming up with models for processes, is they do what I call get married to a model. So they'll come up with a model, and rather than at some point they just continue to tweak parameters over and over and over to try to make the model fit the data. At some point, experience says you need to just say, you know what, maybe this is just not a great model, and we need to even throw out the hypothesis. Maybe it was wrong, and we need to start over and develop a new hypothesis and a new set of assumptions. So anyway, this is basically what the modeling process looks like. Here's an example of a physical phenomenon in physics. It's called radioactive decay. In radioactive decay, we assume that there is a decay rate, dA dt, and that decay rate is actually proportional to the amount of substance that's decaying that remains at a given time t. So, and it's proportional with some proportionality constant k. And so we have then the derivative of A with respect to t, which is its rate of change, actually being equal to k times A. And we also can make an assumption that we started with some initial amount of radioactive substance at time 0, and we'll call that A naught. So this is a first order chemical reaction. Yeah, okay, it's physics, it's radioactive decay, so it's physical chemistry. And so this basically describes, radioactive decay. It can describe other chemical reactions. These are basically rate equations in chemistry. Some of you may or may not have come across that. A lot of times you'll do rate equations, but you'll do them in such a way because undergraduate chemistry, often people do not have a differential equations class. So you'll do them in such a way that doesn't really solve a differential equation. Another example is if you have an edge, a hole at the bottom of a tank, and the tank is filled to some height h. You want to know the volume V that leaves the tank per second. There's a law called Torricelli's law that says that the velocity of the fluid coming out of the tank is the square root of 2gh, where g is gravity and h is the depth. So you can model dV dt is minus some area of the hole times the square root of 2gh. And then V, of course, will be proportional to H, so you can model it that way. In fact, here we go. We say that we have an area of the water surface times the height, and that's the volume with respect to time. And so the only thing there that's going to vary is H. So if we were to substitute AWH for V in that equation, AW comes out as a constant, H is the variable, AW comes out over here. And so this is your equation. Notice that this is a nonlinear differential equation because H, the dependent variable, is actually raised to the 1/2 power. So this would be an example of a nonlinear differential equation that models draining water out of a tank. So I'm not really going to talk a whole lot more about differential equations as models. Just gave you two examples of kind of how that works. There are some, additional things that you can think about and cover, but this pretty much sums up mostly what I wanted to talk about in this lecture today.